we learned a lot from her talks and tours last year's and was one of the best places you want to see. Thanks for in accepting our invitation. I'm really thankful to you with your busy schedule.
I'm glad to give the tour. It's a little different format this year, certainly with the virtual tour, but hopefully we'll do the best we can. So, okay, so as Dr. Grami said, my name is Chris Jansen. I'm the engineering manager here. Have started here as an intern back after my sophomore year, and have worked here ever since. I did spend 1 year at the Mayo Clinic as a project manager, and then came back home. So, CPI is we're a division of Core Molding Technologies, and so I'm just going to go over a quick company overview and then talk a little bit about thermoplastics and what we do here in Winona and what we manufacture. So,
just a quick question. I'm sorry, Chris.
Yep.
Can I record your talk or no? If you have concern, I will not.
Yeah, I think it's okay, but I don't know.
No, if
so as I said,
your company has some concern, we will not.
Yeah, we have some customer owned tooling and stuff in the presentation.
Let's go ahead. I'm not recording.
Okay.
Let's go ahead.
So as I said, we're part of Core Molding Technologies, and we are a custom manufacturer of composites and specializing in products for OEMs. OEM stands for original equipment manufacturer. So if you think of all of the large companies, all the automakers, John Deere, anybody that's going to sell you the end product, they're considered the OEM. So we are headquartered out of Columbus, Ohio. We do have 7 plants through the US, Canada, and Mexico. And we'll kind of show you where all those are here coming up. I apologize. I will say too that I took a lot of this from a sales presentation, so it's a little more sales focused. This just kind of gives an overview of the timeline of Core Molding. The facility started out as a plant it was a Navistar plant for heavy truck. They founded Core Materials, and then over the course of time, they've acquired several businesses. So kind of along this timeline, there's us right there. So back in 2015, we were acquired by Core. And since then, we've acquired Horizon Plastics that does structural foam and structural web molding. But throughout Core's history, starting in Columbus, they've acquired several additional companies to expand their capacity as well as marketplace. So within kind of the Core family, there's a lot of different composite manufacturing methods that Core has and utilizes, from hand layup, spray up, resin transfer molding, reaction injection molding, structural foam, structural web, and then compression molding. And in compression molding, we do SMC, BMC, and DLFT. So SMC is sheet molding compound, BMC is bulk molding compound, and DLFT is direct long fiber thermoplastics, which is actually the part we do here in Winona. But Core as a company has a lot of different processes to offer customers, and it all depends on what they need and what the end use is. As you can kind of see on this graph, as the volume goes up, that method has to change a little bit. Hand lay up and spray up are rather labor intensive processes. They're slow processes. So if we need to produce more, we'll look for another solution for customers. But Core does do thermoset and thermoplastic molding. You guys may already know, thermoset molding is where there's at least a two-part process. Two materials are mixed. There's a chemical reaction that takes place to create that thermoset resin, and that is a difficult bond to undo. Thermoplastics, it's all heat related. So we melt the thermoplastic, mold it, and then we can always remelt it and go back. So throughout core, there's different processes that we can do, some being thermoset solutions and some being thermoplastic. And they have different uses and certainly different environmental impacts as well. So the markets that we support in terms of what we supply products for, we're certainly a very much a heavily automotive truck market. So if you think of large truck manufacturers like Volvo, Navistar, Peterbilt, that kind of thing. So we do a lot of heavy and medium duty trucks, and these are all kind of all exterior panels. We do some marine applications as well. Automotive is certainly a part of our kind of products that we supply. There's also some consumer goods and residential construction parts as well, but there's kind of a wide variety of markets where Core supplies products to. So to get a better idea of kind of what some of these are, like I said, heavy truck, we do a lot of air deflectors, visors, hoods, cabs, and those are all manufactured out of SMC. And they also do some products for buses and fenders and stuff like that as well that are SMC as well. From a thermoplastic side, we have a company, one of our sites up in Canada does a lot of decorative lattice for residential use. They also manufacture some cargo boxes for BRP. We do a lot of watercraft hulls and decks in DLFT as well, and SMC, as well as automotive battery trays, covers, underbody shields. Made some running boards in the past, but kind of throughout all of the industries, there's always probably a little piece somewhere where composites are being used in a wide variety of markets. So our facilities right now, as I said, we have 7 facilities across the US, Canada, and Mexico. So we are in Winona, obviously. The Core does have a site in Columbus, Ohio, and Cincinnati, Ohio. We also have a facility in Gaffney, South Carolina, Matamoros, Mexico, Coburg, Ontario, and Monterey, Mexico are our facilities. And they're all supply similar products in some sense and different products in others based on the capacity and the equipment that each facility has. Our facility in Coburg and Monterey, they do the injection structural foam, structural web molding. So they're the only Core facilities that do that process. And then here in Winona, we only do the DLFT currently. So when we think of why we use composites in what industries and what do they bring, what composites bring to the industry is the ability to reduce weight, to improve fuel economy, reduce greenhouse gases, also can allow for paint-ready surfaces in SMC, as well as flexible design, component reduction. We can take a part that in metal or other ways to manufacture it would be many pieces, and we can turn it into one thermoplastic or thermoset piece, or several pieces that then are bonded together. And then also what we can provide is also a recyclability and sustainability. So we do have the ability to mold natural reinforcement fibers, bio-based resins. We've done some testing with that in the past as well to improve sustainability. So what we do best is we mold really big parts on really big presses for the most part. So with the size equipment that we have, it leads to molding, as I said, large parts and large presses that can have somewhat complex designs and parts that require a high surface finish to allow for finishing and paint processes. We have presses throughout the company up to our largest press in Mexico is a 5,000 ton press. And currently we mold our largest part that we mold on that press right now is just under 200 pounds. And that is in a DLFT part. So we do large format molding. With SMC as well as DLFT, we're able to do, as I said, complex parts that require a Class A finish. There is kind of a difference between thermoset Class A and thermoplastic Class A, but that just means highly visible, high visual parts. And the one benefit too that Core has over potentially some other customers, Core as a whole, and then also what we do here in Winona, is that we custom compound our own material, whether it's SMC or DLFT. So I believe you guys have maybe toured RTP, a virtual tour of RTP or Tycona.
Yes. Yes.
Okay.
And Plasticom.
Plasticom. Okay. So as you saw in those hopefully that materials. And so they kind of have a catalog of materials that they supply. They will also custom compound if needed. But what we do here in Winona and what Core does as a whole is Core, we formalize our own material. So we have our own material, our SMC material as well as DLFT. So what we actually do here in Winona is we compound the material online at the press. And what that allows us to do is then we can basically take that composite recipe and change it however we need to best suit the customer and the process. So because we don't buy pre-compounded pellets from our, say, RTP or Plasticom, we're able to change that, that material formulation kind of on the fly if we need to. If we have a product that runs a little bit better, if we reduce the glass percentage slightly, we can just go ahead and do that, and we don't have to work with a material supplier to come up with another material formulation. So, so here in Winona, we actually have 4 production systems, but in DLFT as a whole across the company, we have 5 production systems. So here in Winona, we have a 1,000-ton press, a 1,500-ton press, a 2,000-ton press, and a 4,000-ton press, which is the one in the picture here. Sorry. Our 5,000-ton press was in Winona for several years. Back in 2018, we transferred that press to Mexico and installed it down there. So actually the 5,000-ton production system is in our facility in Matamoros, Mexico currently. Each of the presses have, when we could, on this slide here, when it says footprint, that's just how big the platen is. So that's kind of if you, the largest piece of steel you could put in there is about that size. That's a constraint when it comes to mold design. And then as is the open height of the press as well. And our production equipment, as I said, is right by the press, and we compound online. So all of our extrusion equipment is sized in a way so it makes sense with the press. So the larger the press is, the larger the extrusion equipment is. The smaller the press, the smaller the extrusion equipment is in terms of throughput. So going through a few, just kind of quickly, some case studies. This is an example of a running board. These were for the Ford F-150s, the regular cab, super cab, crew cab. The original design consisted of a TPO cover. So it's a plastic cover that had a metal substructure to give the running board rigidity and its strength. And it had a bunch of brackets to assemble then to the vehicle, and all of that needed to be assembled into one component as a running board. So that consisted of 43 parts. The design was changed. It was changed to a design that would work well in DLFT, and we got it down to one piece. So we molded this one running board, and that's all the assembly that went into it. So we were able to reduce the components needed and the amount of assembly work that was needed to create a running board. This is, again, when the running board production was here, and in this technology, over 2 million running boards were produced in DLFT. They were able to withstand 3 times the load of the kind of the steel support running board. There was less deflection under load and was a weight reduction of 30 pounds per vehicle, which improved the fuel economy of the vehicle as well. In automotive, vehicle weight is very important. So any weight reduction is a fuel economy improvement. For a time, we also made grill guards for, this is for the Chevy Tahoe and Avalanche. So kind of the interesting part about this is there's the chrome tube that you can see on the grill guard is actually molded on the part. So we would place this one piece chrome tube assembly into the mold, and we would mold the DLFT material over the chrome tube. And the design of the grill guard included attachment points. And so there was no other fasteners or secondary operations required to attach or to have the chrome tube molded in the part. So that was all just kind of a one piece molded assembly. Some of the other things that we're able to do with DLFT is include a lot of different design features. So in this particular part, it's kind of a section of a part, but it's actually an inner cab roof for a John Deere tractor. So in this particular part, we have 52 holes that are molded into the part that are used for attachments and the assembly of the roof components. So this roof piece contains all of the HVAC system, the radio, all your creature comforts that your John Deere cab has and needs. So with this design, they were able to incorporate all the design features in the part needed to make that full assembly, which includes 52 holes where John Deere then, when they assemble the roof, attach all of the kind of the inner workings of the roof. In addition to that, we do install threaded inserts and threaded studs into the part post-molding. So we currently assemble 28 components to this part, which is what is used then to attach the roof to the cab itself, as well as attach some additional features. So there were, of all the holes and all the features that were made on this part, they did have some areas where they needed molded, or they needed inserts as opposed to just attaching components to the composite itself. So we do that as well for this part. Here's another example of kind of component reduction. This is a seed tank lid for John Deere. So John Deere has those kind of big yellow seeders, and the tank has a threaded top. So that's this piece here that we make. It originally was 51 components with all the hardware. So they had the ring, the handles, all the components that attach it, and make up just the lid itself. We took all of those components with John Deere, redesigned that, and they got it down to one piece. this one too, again, this kind of the sales presentation side of this is that from the concept with John Deere to production was a 6-month process to redesign it, have a mold built, and start production. Another part that we make is or had made in the past is a deck for BRP for a Sea-Doo. Several years ago, BRP came out with a vehicle that had the first suspension, brake, reverse, kind of all that fancy stuff. So at the time, this was the largest part we had ever produced. It is a compression transfer mold. I'll kind of tell you more about that here in a little bit. But just kind of another case study of a product we use. So that's a person standing obviously next to it to get an idea of how large the part is. When it's actually on the vehicle, so the picture on the right, it's a little more, it's a little difficult to see where it is once they put everything else on it. But yeah, but the piece is right here. So kind of this big, huge piece, once it's assembled on the vehicle, you don't see much of it, but really what that part creates is that's kind of a floating piece on the deck. It's actually only attached to the vehicle in 3 places. And that's what creates the suspension on the vehicle. As I said, we do other watercraft products as well. BRP, who makes Sea-Doos, came out with the Sea-Doo Spark several years ago. In our DLFT material, we do make the hull and the mid deck of the Sea-Doo Spark. So obviously the hull being the bottom, and the Sea-Doo Spark is what they call a tri-deck system. So there's a front deck, a middle deck, and a rear deck or a mid deck. The part that we make is the mid deck, which is this center section here. And that is manufactured here in Winona. The hull had been manufactured here in Winona for several years, but that has been transferred to our facility in Mexico. Another product that we make for BRP, another hull, it's a compression molded part. It still has a lot of features and is fairly complex for a compression molded part. It is molded in a 30% glass reinforced polypropylene copolymer. We do also mold in a 090 continuous fiber reinforcement. So this particular unit does have, within BRP, they have kind of a large rental market that they supply products for. And as you can imagine, when people rent Sea-Doos, they're hard on them like they are rental cars. And maybe not the most experienced drivers. So BRP was concerned with the impact these parts would see with docks, specifically in the rental market. So we developed a process and a material with them in which we can overmold this continuous fiber reinforcement on the sidewalls of the hull to improve the impact resistance. So as opposed to making a part, as you get thicker in DLFT, you will improve the impact resistance, but you'll also make it heavier. So in an effort to not have to increase the wall thickness, we incorporated this continuous fiber reinforcement that bonds with the composite that's molded in. So, and for this part too, we also mold in die cast engine mount locations. You can kind of see them in the picture, the silver pieces here and the picture on the left. That's actually, we do place those into the mold and mold over those, so they are encapsulated. The mounting locations are encapsulated in the composite material, and that's actually where they mount the engine for the vehicle. Core, we also make out of thermoplastic. We do some work with utility vehicles, cargo boxes and doors for those. We don't make any here in Winona currently, but Core does that. And structural foam and structural web, they, like I said, they do the cargo boxes, so they're replacing steel components. And again, part consolidation and more complex designs with that. We just actually started this product here in Winona. It's a Gator roof for John Deere. So it is the roof. We're making that here in Winona, and also there's for John Deere we do some cargo box as well in the structural foam process. Another product that we make here is have made in the past is a bumper for EasyGo for golf carts. Again, part consolidation down to one piece. Had to have high impact resistance, as you can imagine. Similar to the rental market on Sea-Doos is people using golf carts that they don't own. And again, maybe not the best drivers running into things. So this did have to have impact tests and other in-use tests to eliminate the steel bumper and replace that with a composite bumper. Another product we do for EasyGo is a battery tray for their electric golf carts. This is a relatively small part, but it does have to house 4 large batteries that weigh 75 pounds. This circle here in the picture of the part that you might be able to see, we'll talk about that a little later on when we see the molding process itself. But that is that's actually the puck and the leftover material. So for this particular part, we do compression transfer molding. And in an effort not to have any waste material, after the product is made, we've actually incorporated that, what we call the puck, into the design of the part because it is a non-visual part. We were able to do that, but that probably doesn't make a lot of sense now, but hopefully it will in a minute. Some other products we make, again, for BRP, for their Can-Am division, BRP came out with what they call the Can-Am Riker, which is similar to the Spider. It's just kind of a different cost target. So for that product, we make the frames, which you can kind of see on the vehicle, kind of the main vehicle, or the main framework of the vehicle. And it does incorporate the seat. And I actually have a video of how we mold that, as well as the fenders for that vehicle. So what do we get out of DLFT material and our process in particular because of the way we compound our material? So what we're looking to achieve is uniformly distributed fibers that are completely wet out with no clumping. And what that allows in composites, as you may have learned, is it's all about that interface bond. So we want each individual fiber completely encapsulated in resin to allow for load transfer from the resin to the fiber to improve its properties. So this is just showing a little bit of a side-by-side comparison of our material and a competing material to show. So in the picture on the bottom here, you can kind of see that large white clump. So that's a clump of glass that doesn't have any resin around a lot of those fibers. So that's obviously doesn't have a good interface bond between each of the individual fibers. So that it will have inconsistent properties because the material does change in that area. So that may be a weak spot depending on the test and the use. And it also makes them predictive analysis a little different. So when you're trying to design a product and you're trying to use predictive analysis to determine whether it's an FEA analysis or a mold flow, if you have materials that are inconsistent in properties as well as molding, it's going to be difficult to predict what it's going to do in use. As I mentioned, adhesion is an important thing in composites. So this is just for Dr. Grammy. I'm sure she's maybe the one who took these pictures, actually. So just kind of two side by side. So this is actually an SEM a picture of good adhesion and poor adhesion of a brake in a composite part. So the picture on the left, you can see where you see good adhesion. You don't see the fibers moving or pulling out. No large voids where fibers used to be. The picture on the right, you can see more of fiber pullout and voids in that material. So you have the adhesion on that part is not as good. So the properties of that would be theoretically lower, again, assuming other things being equal of these two parts. So the other thing that DLFT gives us and that we don't see as much in other molding processes is material consistency. So this slide here is just a quick example of a product that we manufacture. This is, as I mentioned earlier, the inner roof that we manufacture for John Deere. This part has a 30% glass target, and that's 30% by weight. So, so in all the areas of the part, no matter where it is, how thin it is, we need that material at 30% glass by weight to get to all of the areas. So on this this slide just kind of shows that distribution of glass and material throughout the part. The numbers in parentheses on this slide, that's the thickness of that area. So you can see in the area on the top left side, that's 29.1% glass. That's a 1 millimeter thick rib. But even in that very small rib, it still has 30% of its content is glass by weight. And you can kind of see then the distribution throughout the part. In other molding processes, SMC being one of them, because of the sheet material that they place into the mold, we can see areas at times where the material is not homogeneous across the part. You'll see resin-rich areas and fiber-rich areas, as that SMC has a little more difficulty flowing and pulling the fibers with it due to the way the sheets are manufactured. So what we do have here when we say a part is 30% glass, 40% glass, 25% glass, whatever percent glass we're trying to target, we do have that throughout the entire part within an acceptable variance. So as you can see, they're not all 30% exactly, but we're all in that glass percent range. The other thing, because we do compound online, and another important part in composites is fiber length. So this is just a picture of what the original part looks like. It's actually a piece of a Jeep door rail. And so what we did is we took that molded part and we put it in our muffle furnace to burn off all of the resin and to show and all that's left then is the glass because it doesn't burn off in the furnace. So you can see on this part here, when we remove all of that, when we remove all of the resin, when we burn all that off, all that's left then is the fibers, and you can see it's a kind of complete fiber skeleton of that entire piece. So there's fibers throughout that entire part, and the fiber length is such that it's able to maintain, the fiber length is long enough to where that's kind of able to retain its shape. So currently the products that we run here in Winona, we run a 1/2 inch chopped fiberglass, and our goal is to retain as much of that fiber length as possible throughout our compounding process. If we break up that fiber or we run with shorter fibers, it will reduce the property. So we want the longest fibers to come out of that process without being damaged. So that's kind of what that picture shows there. And again, this is just part of our sales thing. So we do use, for design, we do a lot of SolidWorks, we do FEAs as well, and we do some mold flow analysis. So in terms of helping us work with our customers to improve the design. I think maybe I didn't mention it earlier, but when I said that we're a custom molder, what that means is we don't mold any of our own products. We don't own the products. We don't own the tooling. They're all our customers' designs. So I couldn't make any of these parts for anybody else. We are under contract to mold these specific parts for our customers and for no one else. So although we don't own the designs, we do assist with our customers with design improvements and changes to best meet their requirements. So the different materials that we use here in Winona, as I said, we do thermoplastic molding. So we do a lot of polypropylene. We've run some nylon in the past, polyurethane, ABS. Again, anything that can be heated, melted, formed, and then remelted is what we do here. The reinforcements that we have run here are glass, carbon, Kevlar fibers, and natural fibers. Currently, everything we have in production here in Winona does run with glass reinforcement, although pretty much anything you could think of to be used as a reinforcement, we've run or tried to run. The weirdest one being chicken feathers. That was tried once. Apparently, that is the only part of a chicken that doesn't get used, which is kind of gross when you think about it. But yeah, we tried to use it as a filler and not much as a reinforcement, but that was probably the strangest one that we've ever run. Don't run that in production. So that was just a trial. So how do we run parts here? So all of our systems for our compounding are utilize two extruders. So what we kind of call the A extruder, B extruder, or resin extruder, compounding extruder. So what we do here is, so we add the resin and additive in one extruder. And what we're looking to do there is to get a homogeneous melt of that resin and additive. And then in the extruder, then that material, the extruder being, for those that don't know, the extruder being really, it's just a big heated barrel with a screw in it, right? So it conveys the material, heats the material, creates shear heat as well to melt that resin into a homogeneous mix. And then that material then is fed into our B extruder. Prior to where the resin meets up, as you can kind of see where the yellow, kind of the yellow arrow here goes. The first thing we put into the B extruder is actually our fiberglass or our reinforcement. So we put that in the extruder first before it meets up with the resin mix coming out of the A extruder. And the reason we do that is because the glass material does have a sizing on it, and that keeps all of the filaments together. So an individual glass filament is very small in diameter. I think we run like 16 microns or something. And it's in a bundle, and there's 1,800 filaments in a bundle. And so we put that in the extruder first, and what it does is it kind of heats up that sizing a little bit and allows the fibers the ability to break away from that bundle. Because again, what we want to get is we want to get resin around each individual filament. So we add the fiberglass reinforcement first. In the extruder, it's in the barrel a little bit by itself. It meets up with the resin mix coming out of the A extruder, and then it's compounded in the B extruder. And so then what the B extruder is doing is kind of gently mixing that resin and fiberglass together to get that homogeneous mix, to get all those individual fibers to break away from their bundles and get completely wet out by resin. Kind of at the end of our system here is we have what we call an accumulator. And all that really is again, it's just a heated barrel with a hydraulic cylinder on it. And so our screws are constantly running. And so during the molding cycle, while the mold is closed and we're waiting to load the next shot of material, we need the material coming out of the extruder that needs somewhere to go. So we accumulate a shot in the accumulator. Maybe not the most creative name now that I say it over and over again, but so what that does is the screws are constantly turning, feeding material out. That the shot or the preform is built in the accumulator. And when it reaches a preset shot size, we have a knife at the end of the accumulator that opens, the piston is activated forward, and that shot comes out, and then we load it into the press. So I do have some video that hopefully will explain this a little bit better, but in general, that's how all of our equipment works. And again, the size of the extruders change based on how many pounds per hour you wanna get out of that system. So, but they all generally work in the same process. So, but first, before we get to that, so now that you kind of have an idea of how that material works, we'll kind of take a step back a little bit and look at the resin blend itself. So what we do have in-house here is we do have a blend station. So what this blend station does is it pulls material from, you kind of see on the right or left of the blue bin on the bottom there, those are either color boxes or other additive boxes. And so what it does is, because we custom compound our material here, is each of our jobs have a resin blend that it needs. It's so much resin versus additive versus a colorant. And so what this station here does is kind of pulls all of those components in and creates a resin blend. So this particular piece of equipment does pull material. We have 2 silos out back that it'll pull material in to these big blue kind of surge bins you can see behind there. And then the operators will go up there and say, I want to make, this resin blend, and it will know how much of each component to put into that blend. So in the end, what that looks like is really just looks like a big tote with little specks of stuff in it. If it's black, if it doesn't have any colorant, it won't look like that. And so it's just a blend of resin, and that much black colorant that you see in there is enough material to color the entire resin blend black. In addition to that, the colorant concentrate that you see, those little black specks, sometimes it's just colorant. It's also other additives. So if materials need UV protection, need heat aging additives, those all of that material is incorporated into that black colorant concentrate pellet. So we start from there. So now that we have a resin blend, now we're going to feed it. So this is a picture of one of our extruders. This is the back side of one of our resin extruders, our A extruders. And in this picture, there's not really a good way to show anybody what the extruder actually does, because it's all kind of guarded in there. But the items that you see kind of above the extruder, these kind of large bins up here, those are the feeders, and everything we manufacture here is fed gravimetrically, which means it's all fed by weight. So in injection molding, a lot of times they'll flood feed. So they have the hopper kind of above the screw in injection molding, and it's just full. And in order to change how much material comes out of an injection molding machine, you need to change the screw speed. So the faster you run the screw, more material comes out. The slower you run the screw, less material comes out. Because we gravimetrically feed here, that means the feeders control how much material goes in. You can turn that screw as fast or as slow as you want to, but the feeders will control how much material goes in. So if we only want 200 pounds of resin mix to go in, we're only going to let the feeders put that much in. If we want more, we'll tell the feeders to put in more. So we don't control that. It's not flood feeding. It's all gravimetrically controlled. And the same is true for our fiberglass feeding. That's all gravimetrically controlled as well. So again, because we're compounding online, the ratio of resin to fiberglass is important for us to maintain. And so all of our feeders are tied into each other so that they know what the other one is doing. So we'll tell it we need so much resin to glass, and the feeders will adjust their speed and feeding amount based on the feedback it's getting. Particularly the glass feeder will adjust based on how much weight it's losing, trying to maintain that ratio. So all of our fiberglass comes in large bulk bags. We open the bottom of the bag to feed the glass, and there's just kind of like a quick video. Not the most interesting thing. But you can see how the fibers, they feed on a vibratory tray that is on load cells. And again, because it's trying to control how much weight it's losing based on the set points that we enter for that particular part or process. So as the fiberglass falls off the end of that tray, the feeder is able to detect how much weight it's losing, and it's trying to maintain a certain weight loss per hour to maintain that ratio. So now that we have the resin in and we have the fiberglass in, this is kind of just a really short video of the accumulator itself. It's a different production system, but just to give you an idea of what that sort of looks like. Because you're not here, you can't really see it. So you can kind of see the heated barrel. You'll see the knives on the end here will open up and the material will come out, I think. So that's the material coming out of the accumulator. That's what we call a preform. So this, it has the resin mix that we saw, and then also the fiberglass all mixed together in a homogeneous mix. So this comes out onto a conveyor that's actually weighed when it comes out, because we do, in all of the products we run, we do have to maintain a glass percentage range or a content range within our customer specifications. So we monitor the amount of glass that we have in the material by the weight of the material. If we get too much glass in the material, the weight will go up. If we don't have enough glass in there, the weight will go down. So all of our products do have a weight range that they run and that we monitor prior to molding. So again, when the material comes out of the accumulator, it is at molding temperature and the glass percentage is verified. It is very hot depending on the material formulation and the set points of the process. So some run at 425 degrees, other ones are up over 500. So, and again, depending on the thermoplastic material as well, that material temperature will change as well. So now that we have a preform, now we got to mold a part. All of our presses here in Winona are vertical presses as opposed to horizontal presses. So if you think of standard injection molding machines, those are considered horizontal presses. Everything we have is vertical. So the two types of molding that we can do here in Winona is what we call compression molding and transfer molding or compression transfer molding. And we'll talk a little bit about that here in a second. So compression molding is, as you might expect. So you take that preform and you place it in the mold cavity itself, and the action of the mold closing is what causes the material to flow and fill the mold. The benefit that gives you is the tooling is relatively low cost. The cycle times are usually a little bit faster. You can do multiple parts in the cycle. You can do molded in inserts. You can kind of do some fancy in-mold decorating. The one problem that you do have, as soon as you take that preform that's at molding temperature and you set it in a mold cavity, that material does start to cool immediately. Actually, as soon as it comes out of the accumulator, it starts to cool on the surface. So generally, compression molding parts are less visible, or less visual parts have not as tight visual criteria for our customers, because you will see what we call a footprint. You will see that cold material that's either come in contact with the mold surface or even the conveyor that the preform comes out on. You will tend to see that on the part surface as well in the compression molding part. Here's just a quick video I took the other day when we were making fan shrouds for poultry barns, as a matter of fact. So in this particular process, there are several, it is a compression molding process. So you'll see the operators lay the preforms in a specific pattern that is designed to maintain the dimensional requirements of the part. So this part being a fan shroud is a large circular part And this preform placement was developed to maintain the dimensional criteria that the customer has for that fan shroud itself. So they will load 5 preforms total in this video. So you can see where they're going to place those, and then again, as the press closes, that is what's going to cause that material to flow and fill the part cavity. So let's see how long this one is. Not too long. So this is after the press opens, you'll see them demold the part. And they're going to place it on a cooling fixture. So that's compression molding. The other type of molding we do here is transfer molding. And this is where we incorporate a hydraulic cylinder into the design of the mold. And so what happens is we load the preform into this, we call it like a shot pod or a sleeve in the mold. We place the material in there, the tool comes closed, the press builds tonnage, and then that hydraulic cylinder is fired. And that firing of the cylinder is what causes the material to flow and fill the part cavity. This process is better for appearance parts that are more complex in their design, parts that have out of draw features. So it's a better process for that. And here's a video. So now he's going to load it into, that's that transfer cylinder he's loading it into. So up until that point, no material has actually moved. That whole preform is still in the center of that tool. And you can hear a little bit in the video, you can hear the press sort of build tonnage. And once it does that, then that hydraulic cylinder fires, and that's what causes the material to flow and fill the mold cavity. So the press at that point is really, it's only trying to keep the tool closed. It's not being used to actually cause the material to flow and fill the cavity. Another part that we had talked about earlier is that upper frame for the BRP Riker. It's a relatively complex part, not very much size or weight to it. I think we mold a right hand and left hand part. The total part weight between the two is about 12 pounds, but it's a relatively complex part and complex mold. The reason I wanted to show this is kind of the benefits of compression transfer molding. So this is kind of the orientation that the part is molded in. And you can see each half of the part creates half the seat. So this is the seat section here. And you can see these openings in the part design. So those are out of draw features. So there's no way to get that hole in the part and be able to get it out of the tool itself, right? So in tooling, everywhere that you see part, that's a cavity. Everywhere you don't see part, a design or a piece of the part, that has to be steel. In our case, all of our molds are steel. So we have to have something that comes in and closes this off so we don't get material in there. And that's all with a tool design that does that. So this is actually the mold that makes this part. And the cavity, this is the seat right here. And you can see the seat is actually two halves that come together, that are forced together as the tool closes to create those openings in that seat area. And then as the press opens, those retract and allow that part to be demolded out of that cavity. So we have, hopefully, so you'll see a little bit as the tool opens, you'll see those move. And all those things that are coming up, those are all pins to allow the part to be ejected. And then the operator is going to load another preform here and then start another molding cycle. So he's loading that in that transfer cylinder in the center of the tool, kind of a far reach. And you'll see a little bit as that tool starts to close, you'll see that seat slide come in. It's a mechanical slide, so pins in the top force that together. We also have hydraulic slides in that as well that also create out of draw features. So it's a rather small part weight-wise, but it is a relatively complex design that we're able to mold. So these last couple slides are just some fun things that we do in the tours that we review, just that we've done in past years, things that people like to see or kind of in awe of a little bit, is how big our molds get. So this is a watercraft part. And I wanted an operator to stand next to the tool so you can get an idea of how big it is. This tool weighs about 100,000 pounds, not our largest tool in terms of weight, but definitely our tallest tool. So this part makes a large watercraft part. The reason the tool is so tall is because it is a compression transfer mold, and we have large hydraulic cylinders that are underneath the mold core itself. So we have to have all that height in order to house those large cylinders. We move these big tools around by a crane. We have a 50-ton crane, which sounds like it's really big until you build molds that are about 135,000 pounds, and you got to deal with them in halves. It's about our largest tool that we have right now. So we do actually have some molds in-house that we can't move with our crane in one piece. So we do have to deal with them in halves. Once you have tools that are that big that can't go anywhere else and have to be lifted by a crane, they have to stay in our crane bay. So they can't leave there because we don't have any way to move them around if they were to ever get out of that crane bay. If you guys were here today, you would get to see some of this. So this is our 2,000-ton press. It's just down on stops right now because we're actually doing some maintenance to it. So here's this is our forklift. It's a 50,000-pound capacity forklift trying to move the slide. Here, if I go back. So this orange piece that you see is either called the ram or the slide of a press. And what they're doing is they're taking that out because they need to do some maintenance on one of the cylinders of the press. So this is one of our maintenance guys trying to finagle this piece in a very small area and not hit the stuff behind it as he's trying to move this large thing. It's a very tight spot, as you can see. So he's trying to swing this thing around to get it out of the way. It weighs about 40,000 pounds is what he's trying to move. Here in a second, you'll see a little bit how tight that space is that he's trying not to hit. So he's got the contractor there. He's trying not to hit any of this stuff here. Definitely a tight fit. So that happened earlier this week. And this is him trying to put that piece down or find a spot to put it. So this is the stuff that not really has to do with composites, but this is all part in being in manufacturing. Sometimes you got to deal with stuff like this. So that's him trying to figure out where to put that thing, the best place to put it. That's me getting out of the way. And as you can see, he can't, because the piece is so large and the forklift is so large, he can't exactly see what he's doing. But that's him trying to take that out of there. And actually what they're doing, so this is actually the piston that they had to take out of the press. That's that big slide piece that you saw them moving before. And what they're actually doing is they're repairing a crack in the sleeve. So that piece was leaking oil, so we had to disassemble all of this so we could bring a welder in and fix that. So that's what actually, if you guys were here today, this is what you would see, is you would see this large piston sitting in our tool area, and you'd see a welder up there trying to fix that crack. What I did find out is we do have a contractor in here who used to work for Williams & White, who built these presses. He did tell me that this large piston here weighs about 14,000 pounds, and it actually was originally a drive shaft on an aircraft carrier. And then when they were looking to build this press, they had contacted the steel supplier, and they realized that they had a decommissioned ship down in the Brownsville, Texas area. So they bought this decommissioned aircraft carrier's drive shaft, machined it down, and turned it into a piston for a press, which I had no idea. That it makes the story of that press much more interesting, knowing that that had a previous life as a drive shaft on an aircraft carrier. So that's all I have for my presentation. I apologize, due to everything. I'm sure you guys are used to it with school, things being a little weird, but hopefully was able to give you some information about what we do here. Are there any questions that anybody has?
It was very interesting. Thank you so much, Chris.
It stands for direct. Yep. Yep. Are there any other questions?
What does DLFT stand for then in general then?
And so it stands for direct long fiber thermoplastics. So the direct part of that being that we compound the material ourselves, that we compound it long fiber, even though we only run 1/2-inch chopped glass, which long is kind of a relative term. In the world of composites, 1/2 inch is considered long fiber. And then thermoplastics being, of course, that's the matrix resin that we use, is a thermoplastic. Yep, go ahead. Right. Yep. So actually, if we kind of go back here, I apologize, so as you can see, when we watch that video, the operator loading the preform into the tool, they're loading it into that cylinder. So when that cylinder fires and that material flows through the runner into the part cavity, after molding, that piece is left over, right? So then that piece gets tossed, and actually, I think in this video, you can see the operator do that. Yeah, right there. So that piece right there, that's actually the same diameter as that sleeve. And then you can see kind of the runner sticking off on the side there. So the operator will grab that. And because we run thermoplastics, and that can all be reground and remelted and used in another product, all of our material actually goes to a recycler. So they toss that, but that's waste material. Now our customers buy that because we sell them a total weight. So that's included in the cost that we are going to have some waste. For that battery tray example, we were able to actually put that cylinder within the design of the part. So for that mold in particular, that hydraulic cylinder is kind of part of the part design. So there is no waste material after molding. There is no, we call it a puck and runner, but there is no puck and runner to scrap because it's incorporated in the design of the part. that makes sense. Mhm.
If students have no question, I ask a question. I noticed that you have fibers of about 3 inches or 75 millimeter for reinforcement. Where do you use them? I can't remember.
So currently in our process, for production wise, we only use 1/2 inch chops, so 12.4 millimeters. We have in the past done some trial work with longer fibers.
Yes.
So because of we don't chop our glass online, so that comes in pre-chopped. So currently our supplier for fiberglass that we use, one of the suppliers of fiberglass, the longest fibers that they will provide chopped is 1/2 inch. Anything above that either would require an online chopping where we pull in rovings through a chopper and then feed it into the screw out of the chopper, or we would have to redesign the screws to pull in fibers and chop. So there are other technologies that do what we do, so that do DLFT work. And they either feed chopped fibers like we do, or they use, other companies use twin extruders that's, if you think of ours are single extruders, so 1 barrel, 1 screw, twin extruders being 1 barrel, 2 screws. So they will use a twin system that will pull in fibers and chop the fibers. The screw will chop the roving. And those generally, so if you want longer fibers, you either have to do where the screw chops the fibers, or you do an online chopping. So we've done some trial work with it in the past. If you can imagine, rovings, that kind of the sizing that I talked about that keeps all those filaments together, rovings have a lot less sizing on them. So if you were to cut that, it's like cutting, I don't know, yarn. I'm sure you guys cut yarn a lot, but like all those fibers, they just kind of all break apart. So chopping online is a little challenging because as soon as you cut that fiber, all the filaments just kind of break apart. It's really the fact that in a roving, it's kind of one continuous piece that keeps that together. So once you start chopping it, all those fibers like to go all over. And feeding material, especially glass fibers, it's kind of like feeding toothpicks if you think about it. So now if you were trying to feed like fur or hair or something like that into a extruder feed throat, it doesn't like to feed, it doesn't flow very well, it likes to bundle up and kind of create big clumps. So it definitely, feeding longer fiber definitely has challenges. So.
Okay, thank you.
Mm-hmm.
Any other questions a student may have? If not, we thank you so much again, and appreciate your time and excellent talk and excellent videos. Really appreciate. This is the last time I am bothering you for this.
That's okay. Thank you so much. We've had a lot of fun over the years giving tours. So yeah, it kind of reminds us all what it was like being students, when a lot of times you haven't been exposed to all this stuff and actual in-use processes. So yeah, and I will say, as Dr. Grami mentioned, she was my professor when I was at Winona State as well too. So if you guys have any questions, or she asks you any difficult questions that I didn't cover, please find a way to contact me and I will help you out. So
thank you.
All right. Thank you guys so much. All right.
Bye. Thank you. So you filled the time perfectly. Thank you.